Okay, another interpretation of the derivative is that it can be interpreted as rate of change. So these are quantities and units that you're familiar with because you have encountered this in physics. Let's go back to the definition of the derivative. So the rate of change of y over the rate of change of x, when you get the limit and make delta x approach 0, that will become dy over dx. That's the derivative. And you're familiar with this delta y over delta x. You know this as y sub 2 minus y sub 1 over x sub 2 minus x sub 1, or simply the slope. So delta y over delta x is the slope of the tangent line. Now another interpretation is that delta y over delta x, so a change in one quantity with respect to a change in another quantity, so rate of change. So in physics, we're familiar with this symbols. So delta d, where d is the distance or displacement, delta t, where t is time, usually in seconds. So what do you think is this ratio? So delta d over delta t, you know that the unit for distance is meter, the unit for time is seconds, so this is quantified as meter per second. And you're familiar with this because you know that this is for the unit for speed or velocity. Okay, so when we're talking about derivatives, so this meter per second delta d over delta t, if you take the limit as delta t approaches 0, this becomes what in physics is called instantaneous velocity. Instantaneous. So that will give you the velocity at that instant, at that particular moment in time. So just to summarize, we have a position function. So by the way, we use in physics to denote position, we use the symbol d because that stands for distance. But here in calculus, we will denote position as s. So why can't we use d? We cannot use d because we might confuse it with the derivative. The symbol for the derivative is the letter d. Therefore, here in calculus, we will denote position. Instead of using d, we will use s. So s of t stands for position function. So it gives you the position of a moving object given anytime. Now, if delta s over delta t, so we get the ratio of this position over time, we know we will get velocity. So take the limit, that becomes ds over dt, right? Or simply, you know that this is s prime of t. So again, it's velocity, right? So that simply means differentiating position will give you velocity. Okay. So s of t is the position function. You get the derivative, you get the velocity function. Now, what if the velocity function, we denote it v of t. So that's the same as s prime of t, the derivative of the position function. What if the velocity is again divided by the change in time? So this time we're talking about the rate of change of velocity over time. You know that the unit for velocity is meter per second, and then divide it by time second. This will give you meter per second squared. And you know that this is the unit for acceleration. Yes. So meaning, once again, if you get the limit as delta t approaches 0, this becomes b prime of t, which is the derivative of v of t. Now, comparing it to the original position function, you have s of t, you get the derivative, you get b of t, and get the derivative of b of t, you get b prime of t, which is obviously the acceleration function, a of t. Okay, so far we have the position function, s of t. When you get the derivative of that, you get velocity. And when you get the derivative of velocity, you get acceleration. Now, comparing the acceleration function with respect to the original position function, this is the derivative of the original function, which is denoted simply as the second derivative. So, you have here s double prime of t. So, that will give you b prime of t, or acceleration. Now, there is another unit now not commonly discussed in rooms, the rate of change of acceleration with respect to time, delta A over delta t. Because your P6 in high school is limited to study of uniform motion or motion with constant acceleration. But in real world, in real life, you know that acceleration also changes. Therefore, we should quantify it as well. Delta A over delta t. You have change in acceleration over time. This will give you a unit called the jerk. J-E-R-K, the jerk. And the jerk is the derivative of A of t. So therefore, the unit would be meter per second cube. Now let's just denote it as A prime of t. This will give you jerk, J of t. Comparing this with our original function position, this is the third derivative, S triple prime of t. Okay. Now, to summarize, okay, so we denote position not using d, the symbol is s. So s of t is position function. When we get the derivative of s of t, s prime of t, you get velocity, the velocity function. So when you get the derivative of the velocity function, that's b prime of t, and that's also the same as getting the second derivative of s of t, you get a of t, acceleration. And when you get the derivative of a of t, that's a prime, you get the jerk, which is the third derivative. This is the third derivative. So subscript, that should be third derivative. That will give you the jerk, the rate of change of acceleration with respect to time. Now let's solve a problem. Suppose a particle is moving according to the position function, s of t equals t to the fourth minus 3t squared plus 4t minus 1. The first question says, what is the position of the particle at time t equals 1 second? So it's simply s of 1. So using the original position function, just substitute 1. So I'll give you 1 minus 3 plus 4 minus 1. So negative 2 plus 4 is 2 minus 1. This will give you 1. So meaning the particle is at 1 second is 1 unit away from its starting point. So let's say the unit is meters, so it's 1 meter. Next question, letter B. What is the velocity of the particle at time t equals 2 seconds? Remember that what we have is just the position function. So to get the velocity, b prime of t, we should get the first derivative of s of t, which will give you 4t cubed minus 60 plus 4. And the velocity at time 2 seconds is simply v of 2. So substituting 2, so that's 4 times 2 cubed minus 6 times 2 plus 4. So you have 2 cubed is 8 times 4, 32 minus 12, 20 plus 4. So we have the instantaneous velocity at time 2 seconds as 24 meters per second. Next, questions. What is the instantaneous acceleration of the particle at time t equals 3/2 seconds? So, differentiating the velocity function which we obtained in earlier in letter B, we get a of t. So we can get the acceleration function. So this is the second derivative of the position function. So you have here 12t squared. So the derivative of this one minus the derivative of 60, which is 6. Of course, the derivative of 4 is 0. So the acceleration as a function of time is 12t squared. Okay, that's 12t squared. So 12t squared minus 6. Now, the question is, what is the acceleration at time 3/2 seconds? So this is equal to 12 times 3/2 squared minus 6. 3/2 squared is 9 over 4. Multiply to 12, that will give you 9 times 3, that's 27 minus 6. So you have 21 meter per second squared. And the last question. The last question is, at what time is the magnitude of the jerk equal to 60 meter per second cube? Now, the jerk, or j of t, is this time the derivative of acceleration. So the derivative of 12t squared minus 6 is 24t minus 0, or 24t. And the question is, at what time is the jerk equal to 60? So we simply equate 24t to that given magnitude, 60. So divide by 24. T equals 60 over 24. And simplifying this, divide by 12, this will be 5 over 2. So meaning at time 5/2 or 2.5 seconds, the jerk is 60 meter per second cube. Okay, so that sums up the interpretation of the derivative as rate of change.